Alrighty, let's get started. Good morning. Welcome to Day 8, Lecture 26. Today we're going to be talking about center and spread. Oh, I had an announcement slide, but it's gone. My only announcement is that the project checkpoint is due today at midnight, so make sure you have that in. The whole project is due Tuesday at midnight. Yes?
Are the slides on here yet?
Let's see. I believe they should be. Indeed they are. Let's check it out. And here they are.
Really? I don't see them on here.
You can try doing a hard refresh. So Command-Shift-R will do a hard refresh. And try that out. But the slides are on there. Yeah, there you go. Cool. So let me start off today's lecture with a little bit of review on confidence interval tests, as well as some clarifications on some questions I had yesterday about using confidence intervals. Okay. So if you recall, we use a confidence interval to create an interval of estimates of a parameter in the population that we're interested in. It's based on random sampling, and 95% is what we call our confidence level, but that could be any percent between 0 and 100. The higher confidence we want, the wider our intervals are going to get. Okay, so we get more confidence but less accuracy. And the confidence is in the process that generated the interval, which means that if I go from population to sample to resample, that entire process will generate a good interval 95% of the time. It's not sufficient just to go from sample to interval. You have to go back to the population and get a new sample in order to get that 95% of the time in there. Yes?
Right. So how come more confidence translates to less accuracy? Is it because of the interval is wider or what?
Right. So the interval is wider, and so we're less sure about where our actual parameter lies within the interval. Yeah. Okay. So let me do a quick demo. So in this class, we've been trying to use real data sets for all this because it's more interesting. But just for today to demonstrate, I want to take a data set that I made up. So here I have a function to do to bootstrap CI mean. So it constructs a confidence interval for the mean. Here I have a fake data set called flips. What I did was I took an unfair coin and flipped it a bunch of times. Okay, so here are some flips. Every time I got a heads, I recorded a 1. Every time I got a tails, I recorded a 0. And this is based off an interview question I heard that Google was giving out a while ago. I don't think they give it out anymore. But basically, the interview question was, I think I have an unfair coin, and I think that the coin is either like 0.6 chance to get heads or 0.9 chance to get heads. How would you decide between the two? And what they're looking for there is not for you to really make a hypothesis test on either one, because either 0.6 or 0.9, like you don't really know. So if the coin is biased, either 0.6 or 0.9 seem equally likely to be good as your null hypotheses. Instead, what they're looking for is for you to try to say, OK, I don't know what it is. I'm just going to estimate it straight up and just get a range of values for what I think the coin is actually biased towards. Okay, so I'm going to show you that. Here's my flips. And it's not defined. Let's try it again. Run that, run that. OK, so here are my flips. And if I group by the heads column, I get how many heads and tails there were. So in this particular case, there were 133 heads and 42 tails. Okay, and I want to ask the question, how unfair do I think my coin can be? Okay, And so all I have to do is, so first let me point out something that I did not get a chance to really flesh out yesterday, which was this idea of using the mean as taking the proportions of some value. Okay, so here I have flips, which is zeros and ones. It turns out that if I have an array of zeros and ones, so 0, 0, 1, 1, so there's an array. If I take the mean of that array, I'm going to get the proportion of ones, right? Because I'm going to do sum them all up, which is 2, and divide by a total, which is 4, which happens to be 1/2, right? So here's 1/2. If I remove a 1, now it's going to count. OK, it's only going to sum up to 1 and divide by 3, so I'm going to get 1/3. So conveniently enough, if I have in my array just zeros and ones, if I take the mean of that, that gives me the proportion of ones. So conveniently enough, we can use the mean to get a proportion. Okay. So in this case, what I'm going to do is take the mean of my flips, column heads. And we can see here that in my flips, there were about 76% heads. Okay, so 76% heads. And now, as usual, I can call my bootstrap CI mean on my flips table. Flips, heads, let's do 5,000 repetitions. And there we go, confidence interval. Okay. So when I have a confidence interval like this, I can say, OK, the population or the coin is probably actually biased to be within this range here. Okay, so the coin is probably about 70% heads, or between 70% heads to 82% heads. I think it's somewhere within that range. Okay. Now, more importantly, yesterday I mentioned the case where we're looking at the bootstrap, we're looking at the confidence interval, and we're checking to see whether 0 is in my confidence interval and how that ties back to like our p-value A/B testing hypothesis test ordeal, right? So in this case, it turns out you can use a confidence interval to conduct a hypothesis test. Basically, if my hypothesis is, my null hypothesis is that my coin is fair, once I construct that confidence interval, I can just check to see whether 0.5 is in my interval. So if my null hypothesis is my coin is fair, then the chance to get heads is 0.5. And I can just look at my confidence interval and see, oh, does it contain 0.5? No. So it seems like my coin is not. My coin's chance of landing heads is not 0.5. Okay. The reason why we can do this is, so let's suppose that our null hypothesis, let's suppose we're running through the normal steps of a hypothesis test. Okay. So we set up our null alternative. So our null is that the coin is fair. Our alternative is that the coin is not fair. And then we choose some test statistic, which is the proportion of heads in however many flips. So we have flips.numRows. So we have here 175 flips. Okay, so proportion of heads in 175 flips. And what do? We simulate flipping that coin, right? So we say, OK, pretend that my coin is fair. Flip it 175 times. Find the proportion of heads. Do that again, keep going, and do that over and over and over again, right? And what do I get? I get a distribution of the proportion of heads, right? So I get something centered at 0.5. So it's going to be centered at 0.5 because we expect 0.5. It's going to go up, and then it's going to go down. That's what we expect if we run our hypothesis test under like the normal null that the coin is fair. In this case, what are we doing? So I mentioned before that when we bootstrap, we pretend that our sample is a population, right? And so you can see that happening here. When I take my coin, or when I take my flips, and I resample for my flips, notice how in my flips, there were 133 heads and 0 tails, right? So every time I pick out a flip from my flips table, every time I pick out a coin flip, it's about 3 times as likely to get heads as it is to get tails. So in a way, when I resample from my flips, what I'm doing is I'm saying, OK, pretend that my coin is actually about 3 times more likely to get heads than it is to get tails. And then pretend that the coin is about that much bias, and then just take flips like that. Okay, so I'm pretending that my sample is a population, and I'm resampling from there, getting samples as if I had gone back to the population and gotten more samples. Okay, and because of that, when I do the normal null alternative hypothesis, my distribution is centered at 0.5 because my null hypothesis was that my coin is fair. In this case, it's going to be centered at my sample mean, right? So this right here, which is my bootstrap, like when I bootstrap, I get a distribution of my statistic. this is going to be centered at 0.76, whatever I got in my sample. That's what it's going to be centered at. But it turns out that the variability here is the same as if I had done the normal null alternative, whatever, right? So if I had done the normal null alternative and I thought the coin was fair, and I took a bunch of samples, because my sample size is 175, I'm going to get the same going up and then down like curved shape if I did my normal hypothesis test as I do when I do a bootstrap. When I bootstrap my sample and get the distribution that way. So the variation here and when I do the normal hypothesis test is the same. That's why I can kind of use either one to do a hypothesis test. Any questions about that? All right, so we can use a confidence interval to conduct a hypothesis test. The idea is that we can use it to test the null hypothesis that the population mean is some number. Alternative is that the population mean is not some number. When we choose a cutoff as a p-value, we construct a confidence interval of 100 minus p% confidence. Okay, so if we say our p-value cutoff is 5%, we want a 95% confidence interval. If our p-value is 10%, we want a 90% confidence interval, so on and so forth. Then all we need to do is check whether x is in our interval, and if it isn't, then we can reject the null. Otherwise, we can't reject the null. Cool. And attendance. I guess it's time for attendance. Let's do it. So again, the link is bits.ly/@-d. I'm going to open it up now. All right, how many guys are sitting in row A? Row A? Row D? Row D, you should know where you are. Row F? Row H? Row H, OK. What about column number 3? Column 3, there you go. 8, column 8. Nice, OK, so you guys know where you guys are. OK, so let me move on. We're going to be kind of switching topics in this class. As I mentioned yesterday, we're wrapping up our discussion on inference, which is basically taking a sample and drawing conclusions about a population. What we're going to do is move on to prediction. Okay, so given some data, given a sample, can we predict other cases? And to do that, we need some building blocks. So today I'm going to be talking about some of those building blocks. We're going to be talking about the average. You guys are pretty familiar with this at this point, hopefully. But if you're not, the way to calculate the average of some numbers is to just add them all up and divide by however many numbers you have. So here I have some data. Take the average 4.25. Pretty simple. Okay. Now the average is not necessarily a value in the collection. Okay. So in this class, we define all our percentiles to be values in the collection. Right? So if I have a collection of numbers, the 49th percentile is always some number from my original data. The mean, or the average, is not necessarily a value in my collection. Okay. In fact, even if my data are integers, the mean is not necessarily an integer, because in this case, I got 4.25, and here's my data. That's all integers. Okay. We know that it's somewhere between the min and max, but it's not necessarily halfway in between the min and max of my data, because in this case, I have the min is 2, and the max is 9. So I expect an average of about 5.5. But in reality, my average is 4.25 because these 3's here are closer to 2 than they are to 9. Okay. Conveniently enough, it has the same units as the data. So when I say the average is 4.25, let's say I'm talking about how many eggs I have in my fridge, right? So 2 eggs, 3 eggs. My average here is going to be 4.25, an average of 4.25 eggs. in my fridge. Okay. And the average we can think of as what we call a smoothing operator. Okay. So what that means is if I had like see here I have 2, 3, 3, and then a 9, which is like really high. If I take the average of all those numbers, that spike in the 9 kind of gets lowered by the average. So the average is kind of lower than my spikes. It's going to be higher than my really strong dips. This is convenient when, for example, you're looking at, say, temperature readings. So you're taking a temperature reading every minute, and sometimes your temperature thermometer will just like spike up or spike down. If you take like the average of every 3 temperature readings, you get something that's a little bit more smooth and lets you see the shape of your temperatures over the course of a day more easily. Okay, so we can think of it as a smoothing operator. It's not super important to know that, but just you'll see that being used sometimes. Okay, so we haven't discussed this in this class, but if you don't know the answer, try to think about it yourself. Let's suppose I have this data on NBA players and their heights. I think I would fall somewhere like over here, unfortunately. I probably won't make it to the NBA. Which is bigger, the mean of this data or the median of this data? Talk it over with your partner. See if you can just reason it out, even if you don't know.
Well, it's left skewed. It's left skewed, which means that more of the data is to the right. So the median is going to be somewhere to the right here. So the mean might be something to the left. It's left skewed. Means that the data on the left pulls down the mean, even though most of the data is on the right end. So the mean end is bigger. Because the mean is effective, it's not robust. It's affected by extreme measurements to either side. So you have something really low that pulls down the mean, even though most of the data are on the right. Right. Robust. You can look over that.
Okay, how many of you guys think the mean is bigger? How many of you guys think the median is bigger? Got like maybe half the class. Let's try it again. Let's get some more hands. How many of you guys think the mean is bigger? Bigger. Okay, excellent. Why do you guys think the mean is? So let's say most of you guys thought the mean was smaller. Why did you guys think that? Kevin?
The mean, as we mentioned yesterday, is not robust, which means it is affected by extreme measurement. So because this data seems to look left skewed, that means the extreme measurements are probably more towards the left, and those pull down the mean, hence leaving the median towards the right in the bulk of the data. That's why the median is greater.
Okay, so you use some terms there like skewed and like pulling down. So basically, you have the right idea. And the way we're going to explain it is basically take a look at this, right? If my data were perfectly symmetrical, I'm going to go over this in just a sec. If my data were perfectly symmetric, the mean and the median would be in the same place. You guys agree? Right. So if it's perfectly symmetric, the mean and median would be in the same place. Now let's suppose that let's suppose I add some values, right? So I have a shape here, a bell curve. And let's suppose I add a value all the way over here, right? So I have a bell curve here that was symmetric, and I add a value all the way over here. What is that going to do to my mean and median? My median, since it's just the point where half my data are on one side and half the data are on the other side, if I add one point all the way over here, my median is probably going to stay basically the same. Even if that point were like even farther, even if it was like out of this room, my median wouldn't shift by too much, right? On the other hand, the more I throw out that point over to my right, the more my mean is going to shift down because my mean is the average of all my points. So you can imagine if I take my point and just like, what direction is that? If I throw it all the way to the south side, right, my mean would probably go like way over there. My median would still be here, right? So when we take our data and kind of shift it around, what you're looking for is the tail of this distribution here. Since the tail is longer on the left side, the mean is more affected. The mean is more affected than the median, right? Because you have more extreme values, as Kevin mentioned, on this side over here. So then, if the data were symmetric, the mean and median would be like probably the same number. And if we add some more values to this side, now the mean goes down more, but the median stays the same. So property of mean and median. You can also think of it as the mean as the balance point of the histogram. So if I went back here and I tried to, if this was like a solid object and I tried to balance it using my finger, I'll like try to find the point where it's balanced, right? So maybe it's like right here. If I add another, if I add another bar over there, I have to shift my finger over quite a bit in order to make that thing balanced again. Okay, so that's one interpretation of the mean. It just so happens that if you work out the physics, if you look at physics and how the balance thing works, it turns out that the mean is actually what you want. So the mean of the mass is kind of like where you want to put your finger. It's not the halfway point of the data. Okay, so it's not just like cut my data in half and put my mean there. That's what the median is. Okay. And as I mentioned, unless the data is perfectly symmetric, the mean is not going to be the same as the median. Okay. In fact, if my histogram is skewed, so when we say a histogram is skewed by when we say the tail is longer in one direction than it is the other, then the mean is more affected by those values that are all the way out there. So the mean gets pulled in the direction of the tail. Okay, so look for the tail. The mean is in the direction of the tail. The median will probably just be in the middle of wherever that data is. Okay. So I have a really quick demo because you guys have seen most of this before. I'm going to turn this off. Is anyone still taking attendance? OK, go ahead. OK, so I have here some values. These are the same values that I saw before. So 2, 3, 3, 9. I just flipped a 3 and a 2. But the mean isn't affected by the order in which my values appear. The way I can calculate my mean is I can do np.average values, 4.25, which is the same as np.mean values. So these are two ways to do the same thing. Or if I forget that these methods exist, I can always do sum of values divided by length of values. And that will give me the same 4.25. Okay. Another way to think of the mean is what we call a weighted average of however many times the thing appears. So for example, here we have 2 appears once, 3 appears 2 times, and 9 appears once. So what we can do there is take the proportion of values, the proportion of times each number appears, and multiply and then add like this. So 2 appears once. So it appears 1 out of 4. The proportion of times that are 2 is 1 out of 4. And then 3 appears 2 times, 3. And then 9 appears once. That's 9. And you get the same thing, 4.25. Okay. This is convenient when like I don't have actual like counts here, but I just have a list of numbers and however many times they appeared in my original data. So for example, here, if I group, here in my group, I don't have like zeros and ones. I have 0 appeared 42 times, and 1 appeared 133 times. I can still find the mean as long as I know however many times the number appeared. Okay, so that's about it for mean. Any questions? Cool. All right, now are we done? Anyone still going? Cool beans. Alrighty. All right, so now you'll notice that if I have 2 distributions, right, and they're both perfectly symmetric, so the mean and median are the same, and they're centered at the same point. Okay, so if I have one distribution that looks like this, like a really wide distribution, and one that looks very narrow, but they both are symmetric and they're both at the same point, using the mean and the median, there's no way to distinguish between those 2 distributions. So we need another measure. And in this case, what we want to do is we want to say, OK, we have 2 distributions. One is really wide, one is really narrow. If they're centered at the same point, but one of them is more spread out than the other one, I want some way of measuring that. Okay? So we use what we call a standard deviation to measure the spread of how wide I can expect values to be given a distribution. So we want to define variability. One way to do it is to take the biggest value minus the smallest value. But indeed, it doesn't provide information about the shape of my distribution, right? So even if I have one really wide one and one really narrow one, if my narrow distribution just happened to have two values that were like really far apart, I still wouldn't be able to tell the difference between those two distributions. I want something that measures more of like the overall spread. And so what we're going to do is say, OK, I noticed that in my spread out data, I have more values that are far away from my average than in the case I have skinny data. Okay? And so I can measure that. And the way we do it is this. So we have here, I'm going to take my values. Here is the average of my values. There we go. Okay. What I'm going to do is I'm going to say, OK, I want to figure out how far away each value is from my average, right? Because the more spread out my points are, the farther away they'll be from my average value. So take my values, deviations equals, I'm going to make this an array, 3293. Okay. I want to do a subtraction. So I want to take my values, subtract out that average. So here is my average. Subtract out my average. Here are my deviations from the average, right? So here I say, OK, 3 was negative 1.25 away from 4.25. 2 was negative 2.25. 9 was 4.75, et cetera. So I've just done a subtraction. Put those into a table, just so you can see that. T equals table. Call this value. And call this deviations. So here we have this table. All right. So one thing we can do is we can say, OK, I have here some deviations. I can just sum them up, and hopefully that'll give me some measure of how spread out my distribution is. But when I try to do that, it won't work. Right, column 1, okay, dot sum. We get 0. And in fact, every time you do this on any data set, your deviations will always sum to 0. Okay, you can work out so it's like a little algebraic manipulation you can do to kind of prove that. But you'll find that no matter what data you choose, if you take your average and subtract out all the values from the average, you sum up those deviations, you're going to get 0. Okay, so we need some better way to do this. And the way we can do this is we can just square each value to make them all positive. So the reason why it's 0 is because these negative values happen to cancel out this one positive value. What we can do is we can square all the values to make them all positive. And then we can add them all up. Okay, so I'm going to take my deviations, which is this array, and square it. Here it is. Now I can add my squared deviations. So let's add it to my table. Column, squared deviations, add in there. Bam. Okay. So now we have these values, which are all positive. Notice that my 9 here had a pretty big deviation, so a squared deviation is really big. Yeah, Elliot?
The sign, is there any other reason why we would square it? Like, why don't we just take the absolute?
Yeah, why don't we just take the absolute value? So there are some important mathematical properties that comes from squaring. I won't go over why in this class, but if you take more stats classes, they'll teach you why. Yeah, but it turns out that squaring it gives us a lot of benefits down the road, including some interesting inequalities that I'm going to be talking about later on today. Yeah, so squaring it does have some value. It's just convenient mathematically. So in reality, there's no real. So if you're just looking at this and you just want to find the deviations, you didn't have to do the squared. But it just happens to be that if you square it, you can use that number to make some more conclusions down the road. Yeah. Okay, so here I have some squared deviations. I'm going to sum up those and find the average. Okay. So I want to find the average squared deviations. Let's add that to my table. Or actually, I have this. I'm going to save this in a variable because I just want this. Okay, let's call that squared deviations. Put that there. Okay. And then I can just find the mean of those. And that gives me 7.68. This is what I call my variance. Okay, so this is, in statistics, the term, when you hear the term variance, this is how to calculate it. Find out how much each number is away from the mean, square those deviations, then take the average. If I want to find the standard deviation, which is another statistic term, we would do SD equals NP of square root of variance. And let me just show you that. In this case, we'd say in my data, the standard deviation is 2.77. Okay. Now, it's just a number. It doesn't mean a whole lot to you just yet. But if you notice here, if this 9 were instead, let's say, 109, then this deviation would be really big, right? And the square deviation would also be really big, which means that my standard deviation will also go up by a lot. Okay. So indeed, if my data are close together, then my standard deviation will go smaller. If my data are really far apart, my standard deviation gets bigger. So that gives us some measure. So basically, we can say the bigger the standard deviation, the more spread out my distribution. Okay. And it does take into account all the numbers in my distribution, right? So I have here my entire data, which means that even if I had the case where I have really spread out data and really narrow data that just happens to have 2 points on the ends, I can still measure that difference with standard deviation. Cool. Any questions? All right, excellent. So here we go. So the standard deviation measures about how far away the data are from the average, right? So what I did there was I took the deviations and I squared them. I did some extra math manipulation. But the deal is I'm using how far away my data are from my average to try to get a measure of how spread out my distribution is. Okay. In fact, the standard deviation is defined as the root mean square of deviations from the average, which is really long and complicated. But if you read it backwards, this is basically just what we did just now, right? So we have the average. We found the mean, found the deviations from the mean, squared them all, found the mean of that, and then took the square root, which is really long and complicated. And if you don't want to do all that whole steps, again, you can just do NP dot standard deviation, and this will give you a standard deviation. So here I can just do standard deviation of values, and save you a bunch of typing. Okay, so this thing does the same thing as doing all of these cells up here. So if you want, so just remember this, but know that if you forgot how to do the standard deviation method, you could just do all this work. Okay, cool. So conveniently enough, so the reason why we take the square root at the end is because that lets us say the standard deviation has the same units as my data. So if I were to just leave it as a variance, which is like right before the square root, if you work through the units, you kind of get some weird units. So if I take however many eggs I have in my fridge, then the variance has units of eggs squared, right? So if I had like 3 eggs on Monday and 2 eggs on Tuesday, and I bought more eggs and 9 eggs and I use it, so if I had those eggs in my data, and I do this calculation, but I leave it as a variance, so without taking the square root, my variance has units of like 7 eggs squared, which is not very interpretable. So instead, if I take the square root, now I have something that's like 2.77 eggs as my standard deviation. This lets us say, OK, average amount of eggs in my fridge was about like 4 eggs, plus minus a few standard deviations. It's kind of a weird expression to you right now, but I'm going to go over why that's useful in just a little bit. Okay, so we're done for the first half lecture. Excellent. We're on time. Go ahead and take a 5-minute break, and then we'll continue.